start now. Awesome. So, hello everyone. Welcome to the CITA seminar. And today we're great to have our very own CITA National Fellow, Alex, coming to give us a talk on testing the H0 and sigma intention with galaxy survey and large-scale structure. Just to introduce Alex a bit more. So before he joined us as a CITA National Fellow, he is also the ANTD Fellow at the University of Waterloo, and he did his PhD mathematically. Alex is a DEXI member, so with the recent DEXI paper coming out, please ask him about any insider view on that. And he's also a member for the Simon Observatory and also at CMBS 4. So please make the most of his visit here to bug you with all the questions. And Alex is happy to take questions during the talk too. So without further delay, take it away.
Okay, thank you very much for the nice introduction. All right, so I wanted to start with this sort of somewhat provocative view of large-scale structure and cosmology. And I really want to, I know I'm putting up this slide here as motivation. I really want to emphasize, though, that we see some tensions in our cosmological observations today, and there are, in some cases, the H0 tension is quite significant. But I don't, overall, Lambda CDM is a very highly successful model at fitting CMB and large-scale structure data, and so I do not think it's time to move past it. I want to merely take the tensions that we see as motivation for better examining our data, for systematics and other sorts of assumptions that we made to really make sure that we understand the analyses as well as we can. So here on this slide, I'm showing your standard, the classic evolution of the universe picture, and then I'm highlighting some of these tensions that we've seen, the Hubble tension between CMB and local distance ladder measurements of the Hubble constant, this tension in the growth of structure around redshift 1, and then, of course, as Jennifer just mentioned, there's this hint DESI favoring non-lambda CDM cosmology involving dark energy equation of state. And I put that up there just to advertise the fact that I'm part of DESI and that I'm happy to talk to people about this result, but I won't be talking about it in the talk. And I think put some question marks there because I think it's not, it's quite dependent on the data set that you use. I wouldn't, I wouldn't read too much into this, but I think again, these are things that we have to understand better. And then I've also highlighted neutrino mass as another observable that we're looking to constrain with cosmology today. And I wanted to put it there, in the context of these tensions, in that we really want to understand what's going on with our data if we want to be able to say something about the mass of the neutrino and really make it believable for a particle physics audience. So there's no tension with the neutrino mass, but I wanted to have it there as motivation. So, right, so in this talk I have kind of two sections where I'll talk about first this amplitude of structure tension and then the Hubble tension. So the S8 tension here, this is sort of a slight discrepancy between the amplitude of the matter power spectrum as measured by the CMB and is measured by mostly weak lensing surveys. And then the Hubble tension I have circled at the CMB to sort of emphasize the model dependence of the cosmological results. I don't want you to take this as some statement about the CMB being wrong. It is merely saying that if you were to modify the model in some way, the best way to do it is by modifying pre-recombination physics. So I will talk about some observations that we can do that can test models that are changing this pre-recombination physics. Okay, so starting with the first part about the S8 tension. So this is a number of papers that I've been working on measuring the amplitude of the matter power spectrum and really testing this S8 tension with CMB lensing cross correlations. And there are a number of great collaborators that I've worked with. I think you heard from Garrett this fall, so I will try to keep this part brief and sort of as an overview of what we're doing and where we're going, and I think he mentioned many of the technical details of this analysis. And so just as a reminder for everybody, what we're trying to measure. So, of course, gravity bends light that's emitted by distant galaxies, and this is showing a sort of the strong lensing setup where you have a very highly coincidental alignment between a distant galaxy and the lens. Weak lensing is like this, but for all galaxies and not with this nice alignment. So you're really seeing the distortion of all photons that are not necessarily passing very close to the lens. And you're seeing the distortion of those photons from all matter along the line of sight. All right, so the parameter that we talk about with weak lensing is this funny S8 parameter. And so where exactly is this coming from? So when we measure lensing, we're measuring the amplitude of lensing, which is giving you some information about the amplitude of the power spectrum times the amount of matter. And the amplitude of the power spectrum is controlled by sigma 8, which is the redshift zero normalization of the linear power spectrum on small scales. And so this is, sort of schematically where this dependence is coming from. So P of k goes to sigma 8 squared, and then the amount of matter gives you the omega m. More technically, we have the limber equation, so you're integrating the power spectrum along line of sight, weighted by some lensing kernel that has cosmological parameter dependence itself. So this gives you this characteristic S8 parameter that is best measured by weak lensing. Right, so here's what happens when people have gone out and measured S8 for a number of cosmic shear surveys and compared it to the CMB. So CMB is this band. And then on top, there are a number of different weak lensing and weak lensing combined with galaxy clustering. And so, of course, it's very striking that all of these measurements of the amplitude have come out low. But I do want to emphasize there's a significant caveat here. Many of these measurements are correlated, so some of them are actually the same survey, or the same, different versions of the same survey, so they have a lot of sources in common, as well as there are some correlated assumptions, correlated systematics arising from the sort of same modeling assumptions made even between different surveys. So this means that doing a joint analysis is quite non-trivial. So for instance, the kids' desk joint analysis was really a lot of work, just unifying these modeling assumptions and making sure that those are done in the same way. And so, basically you can't really just take all these points and add them up and get some insanely large tension. That's not correct to do. Overall, this is sort of pointing towards a 2-ish to 3, so a 2 to 3-ish sigma deviation from this low redshift structure amplitude. And I should have clarified that by low redshift here, I mean compared to the CMBs, this is like redshifts half to 1. And so, maybe depending on your definition of the word tension, it's not even really a tension, but it does seem like something is consistently driving all of these surveys, these cosmic shear surveys, to find a low amplitude. So our work, we were motivated by this situation, and we wanted to measure the CMB lensing cross-correlation as an independent probe of low redshift structure growth. And the advantage of CMB lensing cross-correlation is that you can measure really large and high redshift modes. And these are modes that are modeled well by linear theory and are therefore easier to model. In practice, we model them perturbatively, but the fact that they are closer to being linear makes the perturbation theory work better. If we're looking at lensing of the CMB rather than lensing of distant source galaxies, there are very different and therefore largely independent systematics from both cosmic shear and 3D galaxy clustering. So we could basically provide an independent perspective on what's going on with the amplitude. Right, so So with CMB lensing, we have a similar situation with galaxy lensing. All the CMB photons will be in gravitationally lensed as they propagate across the universe. And we can detect this from their particular imprint on the observed CMB. So the unlensed CMB, you see over here on the left, has very Gaussian statistics, and the change in CMB temperature and polarization from lensing has a very distinctive non-Gaussian pattern. Right? So you can see, even though this delta T is relatively small compared to the CMB temperature, its statistics look very different. And so we can write down a quadratic estimator that takes advantage of this difference in statistics to extract a map of the lensing convergence from the temperature shown here, as well as from CMB polarization, which is now becoming quite important for the current generation of CMB experiments. The other important thing to know about current CMB lensing measurements, so first of all, the geometric CMB lensing kernel, it goes out to quite high redshift compared to cosmic shear because our sources are at redshift 1100 rather than being galaxies at redshift of 1 or 2. So this means that sort of the geometric kernel peaks around redshift 2, so we're quite sensitive to high redshifts. The best CMB lensing measurements come from very wide areas of the sky. So Planck is an all-sky survey, so we see everything except the mass galactic plane. ACT DR6 also has a very wide field of view, although not the entire sky. High redshift and a wide area. So the CMB lensing on its own is great, but we can do even better if we add galaxy information as well. And this is because basically the CMB lensing measurement is giving you a measurement of the integrated matter density along a line of sight weighted by this lensing kernel, which means that you can't really tell the difference between redshift 1 or redshift 5 or something. It's all being mashed together into the lensing kernel. So by instead cross-correlating the CMB lensing with galaxies, we can isolate different redshifts and tomographically map the structure growth as a function of redshift. Additionally, the cross-correlation has more signal-to-noise than the autocorrelation itself. So we can add cosmological information and break some degeneracies. And finally, this cross-correlation is interesting because it allows us to isolate the same redshifts where we're seeing this low lensing amplitude from cosmic shear, isolating redshifts of around 1. Okay, so what galaxies do we use? So I already said that the CMB lensing maps are large areas and a high redshift, so we want a sort of matching galaxy catalog. And it turns out that one of the best ways we can do this is by using infrared galaxies imaged by the WISE mission. So WISE is actually, it's quite a small telescope, so it's only 40 centimeters. It's not that big, but it has some big advantages. So it is an all-sky satellite mission, so it has very low background and has very high, sees the whole sky. And as an infrared survey, it can take advantage of the fact that sort of old stellar populations, and therefore luminous red galaxies, are quite bright in the infrared. So just as an example, this is a redshift 1 luminous red galaxy in SDSS on the left and WISE on the right. So you can really see that it's picked out quite nicely in these infrared bands. And so these characteristics have allowed us to make a very large catalog of 500 million galaxies at all the way out to redshift 2. And again, because of this, basically because of where we're looking in the infrared, where we're actually quite sensitive to higher redshift galaxies, which is really quite good for the synergy with CMB lensing, which is benefiting from having a coverage of quite high redshift. Okay, so we have this awesome sample of galaxies. How do we go about cross-correlating it with CMB lensing? So we start by splitting our galaxy sample into a few tomographic bins. spanning redshifts about 0.5 to 1.5. So we can define 3 samples using this 2-band imaging, and then remove stars using Gaia. So we're left with very low very small amount of residual stellar contamination. Yeah, so the main cosmological information from the sample is coming from these blue and green samples, which are, as you can see, they're considerably denser, and the red sample currently has very low density, so it's not of much use, but in the future, since WISE continue to gather data, we have considerably more galaxies now in this red sample that could be quite interesting in the future. All right, great. So I'm telling you all these advantages of WISE, but there's one really huge disadvantage, which is that it is a 2-band, it is only a 2-band survey. So photometric redshifts to determine the redshift distribution are totally impossible. There's just essentially no information beyond these 3 very broad bands that we can get about the redshifts of individual sources. So we instead need a very different approach. And so what we do, oh yes, and so another thing that you might want to do, okay, so you can't get photometric redshifts with the 2 WISE bands, but what if you instead cross-match to very deep photometric or spectroscopic redshifts? So you can do that, but these surveys are only available in very small areas. Basically, people are not usually targeting these sorts of infrared selected galaxies, so you need quite a deep optical survey. And so that sort of a measurement would be highly affected by cosmic variance only for the small areas available. So instead we use clustering redshifts. So the idea here is instead of using color information, you're using clustering information to get the redshift. So you take your photometric sample with unknown redshift distribution, and you cross-correlate it with a number of spectroscopic samples in very narrow bins. And so you repeat this across a number of these narrow bins. And the amplitude of that cross-correlation in each bin is proportional to the overlap in photometric redshift. In other words, it's proportional to the fraction of the unknown sample that lies in that redshift bin, right? This makes sense. If the galaxies lie at the same redshift, they will have a stronger clustering. And so doing this, we can build up the redshift distribution. And in fact, you'll notice that it says dndz times b. So this is also sensitive to the clustering bias of the galaxies. Of course, the more biased the galaxies, the stronger this clustering signal. And this is convenient for a CMB lensing cross-correlation because you care about both the redshift distribution and the bias evolution of the lens galaxies that we're using. And so here, this figure is showing the clustering redshift distribution that we've measured and comparing it with this tomographer, publicly available tomographer tool. The agreement is very good. Tomographer has less conservative data cuts, which is why it has those smaller error bars at about redshift 1. But yeah, I mean, the agreement here is just within the error bar, so it's quite good. And of course, this clustering measurement is noisy, but we propagate this error into our cosmological constraints, and it makes a non-negligible contribution to the error on parameters. Okay, great. And so we also need to make sure that the fluctuations that we see in the galaxy survey are purely cosmological, and they're not driven by systematics, right? Because we want to use the galaxies as a tracer of the matter distribution. And so to verify this, we took the density of galaxies and we plotted it as a function of various systematic properties like the density of Milky Way stars, or the depth of the survey, or the column density of neutral hydrogen. It turns out, as you can see on the left, that there are quite significant trends between the density of these unwise galaxies and these different contaminants. And so we remove these trends. Basically, we fit a piecewise linear function to all of these. Actually, we fit a piecewise linear function just to W2 depth and star density, so just the two that you see here. And this largely removes the trends that you see with those properties, as well as a whole bunch more that could not fit on this slide. But we had like 10 different maps that we checked, and in all cases, the trends were looked much more consistent with being uniform after applying the weights. And also importantly, we can look at the clustering of the weighted galaxy sample. We see that the weights have little impact on the galaxy clustering or the galaxy seen events of cross correlation. And this is after throwing away large scales which have a larger contamination from these angular systematics. But this is also good because it means that this sort of additional, so you might say, oh, there's a little bit of a trend in the stellar density that you can see up on the top. But given that already the weights have had a small impact on the clustering, adding sort of extra weight should be even smaller. Okay, great. And so then we made a cosmological measurement. And so, this is the interesting part here. And the combination of unwise galaxies with ACT and CMB lensing gives a value of S8 that is consistent with the primary CMB and higher than what's found by weak lensing surveys. It's not entirely inconsistent with either, since it's sort of in between at 0.81. We can also break this sigma 8 omega matter degeneracy by adding the AO information, and this yields a similarly tight constraint on the amplitude of the power spectrum itself that is also quite consistent with the Planck value. We should point out that this result on S8 has shifted upward about 1 sigma versus the previous Planck cross correlation. And this is due to basically a variety of different improvements in the analysis pipeline, almost all of which tended to increase the value of that S8. Okay, so here's this result on the top compared to a number of these other lensing results for S8. And as I was saying, we're generally favoring higher S8, closer to the primary CMB value that's in pink down at the bottom. That is sort of interesting. And so given that we're using somewhat larger scales than the cosmic shear measurements, it suggests that maybe there's something interesting going on small scales. But then again, the sort of level of disagreement here between the CMB lensing and the cosmic shear is not terribly significant. So it's, it could just be statistical fluctuations. Okay, so this is all great, so what's next? What can we do in the future? So first of all, as I alluded to earlier, WISE has continued to gather more data. So the data set that we used had 5 years of observation. And while we were doing the analysis, WISE has been working away, and now we have 10 years of observation. And so now, basically I've just taken this selection plot and, pointing out that the faint cut that you see here can be extended quite a bit further down towards fainter magnitudes. So we can have even larger galaxy samples. This is not going to hugely change the signal to noise that we would get, because we already have such high number densities that the measurement is cosmic variance limited. So there's not much to be gained from increasing the density, further increasing the density of galaxies. However, it's always good to have deeper observations to enable better systematics checks and to make, basically make the same catalog at a higher signal to noise, and therefore the detections that you have are more robust, and less prone to fluctuations due to the depth of the survey. More importantly, by increasing this depth, we're really going to have a lot better coverage of this high redshift sample, which we didn't use for the cosmological analysis because it was much less constraining than the other two. And so that is exciting because it basically means we could sort of push this measurement out to a higher redshift and have sort of another tomographic look at the growth of structure with 3 bins out to redshift 2, and of course you have the cross correlation with you have the CMB lensing autocorrelation itself as another probe of the redshift greater than 2 that we're also have some dedicated DESI time to measure the unwise redshift distribution. This is also helpful in sort of better constraining those clustering redshift distributions that I showed. This is a preliminary plot, which looks quite consistent with the photometric redshift distributions that we already had. Of course, our clustering redshifts, I was using WISE cross-correlated with SDSS galaxies, but now we can update those using DESI, and so again, this will help shrink the uncertainty on the redshift distribution and therefore improve the constraining power on the cosmological parameters. And beyond lensing, there are a number of other really exciting science applications of this sample. I mean, basically, what is good for cross-correlating with lensing is also good for cross-correlating with other CMB observables, since they all also benefit from the whole sky and high redshift coverage. So we have some constraints on dark energy from the integrated Sachs-Wolf effect. We have KSZ measurements. This is basically looking at projected bispectra instead of using the redshift space clustering. That this is allowing you to measure the gas profiles and baryon fractions around the unwise galaxies. We have some measurements of their halo occupation distribution, both modeling the autocorrelation and CMB lensing cross-correlation, and also modeling, directly modeling the cross-correlation with spectroscopic galaxies. You have some constraints on the redshift evolution, the HOD. And another, I think, very exciting paper I wanted to highlight was this unwise CIB cross-correlation, which has a combined significance of 194 sigma, and I've never seen a detection significance that high. So that was fun. And yeah, actually there are a number of other things that I couldn't even put on this plot. But basically, yeah.
Can I ask you about the unwise pod? So does that mean that you've actually got some kind of measure of the bias of galaxies relative to the dark matter and halos?
Yes. Yes.
So is that a formula that's available now and with appropriate errors?
It's the I don't think that the best fits are available and the error bars are available, but the parameters are covariant.
I don't understand, but you mean that they're just correlated. So.
Yeah. The HOD parameters.
Look, maybe I could put it another way. Have you embedded this in a theory of exactly how that should look within a halo?
Yeah. So this we have both like a halo model analytic calculation, and we've put this halo model into n-body simulations and predict the projected clustering, autocorrelation, and cross-correlation runs it.
Would you need to be a hyperdynamic simulation?
No, because these are just like effective parameters saying, occupy all halos above a certain mass with some power law slope with satellites. Like it's only tied to the dark matter.
Yeah, it's the shape that I'm interested in here, relative to the, let's say, that stuff.
Ah, okay, yeah, like the small scales.
You know, within the halo itself, not some sort of global average where it's just a counting thing. I mean, not that that's not important to do, it's extremely important. But I've always felt that there wasn't enough effort going on to actually we call them response functions around here, and lots of people in the audience are experts on this. But it would be really good to improve those halo occupations. So you might have, for the use of where the galaxy is.
Yeah.
And it's curious that as far as I can see, there hasn't been a huge operation on this because it's sort of at the core of these very large surveys.
Right, no, I definitely agree that it would be interesting to look at better modeling. Actually, this middle panel, this redshift evolving HOD, we actually have measurements down to quite small scales. That's harder to do with the CME lensing cross correlation does not go to scales that small. So yes, it'd be interesting to connect it to better simulations.
What is it with the CIB that's 194 sigma?
So the CIB itself is detected at very high significance, and then we have a very high density galaxy sample. So in all the other cases, we're limited by the other, CMB secondary, like the lensing is, ACT. Yeah, there's not, I mean, the lensing noise is relatively high on small scales. The CIB noise is quite low, measured at very high significance.
What data product contains the CIB?
Planck, high frequency, 353, 545, and 857 gigahertz.
Well, it's a good map that the CIP out of Planck is inhomogeneous in the sense that you do a cross with, try and do a cross with H1. So there is probably not full coverage of that. Did you use the full Planck map of the CIP?
I don't know the details. I think that maybe the 194 is like a full area, and then they model a small area. But yeah, I wasn't on this paper.
And one thing that can be done with this, because the data is so good and the detection is so amazing, you can actually use the unwise and actually try and do what is in effect tomography on the CIP. And have you looked at that?
I think in that paper they looked at it a bit. I mean, so one of the challenges is that we really only have these like 3 bins to do. Like the WISE galaxies can't be localized much better than the bins that we have, which are rather coarse.
Well, they can. Yeah, okay, good. Yeah, but okay, so only 3 basic redshift bins.
Yeah.
And so it's photometric and it's therefore quite elongated. And, yeah,
Right, okay, and then this was semi-related, but I figured while I was talking about CME lensing cross-correlation, I might as well also point out that CME lensing cross-correlation can provide a clean way of measuring ultra-large scales and therefore constraining primordial non-Gaussianity. And so the idea here is that we're looking for a scale-dependent bias signal that can be created by local primordial non-Gaussianity, by the influence of primordial non-Gaussianity on halo formation, and a large value, or a value of this FNL parameter greater than 1 would be inconsistent with predictions from single field inflation. And these large scales are difficult to measure with galaxy autocorrelations due to systematic effects, as I was talking about earlier. So these sort of associations with imaging, even if you can try to take them out, but they still may be large residuals that you don't fully understand. And so the cross correlation offers a cleaner view of these large scales. So we cross correlated photometrically sampled quasars with CMB lensing as sort of a first demonstration of trying to do this. This is a sample that had a ton of extra noise in the autocorrelation. Like we basically treated the autocorrelation of these quasars as noise. Like it was, we're not going to try to model it at all. And we just modeled the cross correlation, and we're able to sort of get reasonable cosmology and robust various different systematics tests. So this is, we're a long ways away from the precision where we want to be, but this is something that I'm quite excited about in the future with further higher redshift galaxy samples, higher redshift and higher density galaxy samples than the ones we have today. Okay, so now I think I should go on to part 2 because a little more than halfway done. So this is a second set of measurements and papers that I've been working on that is a different area. So we have, with Will Percival at Waterloo, we've been working on developing a new method to measure the Hubble tension, the Hubble parameter via energy densities as a way of testing solutions to the Hubble tension that change pre-recombination physics. And so of course everybody knows that the Hubble parameter is sort of diverged between the distance ladder and the CMB measurements. And of course there are many possible things that could be going on here, and I want to use this work to explore a set of possible solutions, but not to really say that it can't be something else. And so the particular observation here is the fact that the LSS H0 measurement depends on the model for the early universe. And so people have asked the question, can we resolve the tension by doing something to the cosmological model? And so to answer that question, it's just a review of how we constrain the Hubble constant from CMB. And ultimately it comes down to the angular position, the angular sound horizon, the position of that first acoustic peak. So the CMB has these acoustic waves that are set up by the opposition of gravity and photon pressure, and that set up this very well measured acoustic structure. And so the position of that peak is given by the distance that a sound wave travels between the Big Bang and recombination, divided by the angular diameter distance to the surface of last scattering. And so given that we can measure the sound horizon RS very well, that means that we can infer the angular diameter distance to last scattering and therefore measure the Hubble constant. And so, in other words, the Hubble tension can be recast as a sound horizon tension. So this band here is the orange band on top is the Shoes constraints, and you can see that there's this divergence, and if you could do something to change that sound horizon to make it smaller, you could bring these measurements into agreement. And so this is what people are doing when they propose models like early dark energy. So the sort of best cosmological solutions to the Hubble tension are models that modify the sound horizon. So this is a plot of the early dark energy fraction as a function of redshift. The red line is roughly recombination. And so you can see that basically we've added a new component that's about 10% of the energy density of the universe close to recombination. And this is going to increase the expansion rate and and therefore decrease the sound horizon. So you get to the sound horizon faster, make it smaller, and in that way it can alleviate the Hubble tension. And this is, one of a few of these models that people have proposed that change the sound horizon. So other models doing things like varying the recombination history or adding primordial magnetic fields, etc. All right, so with galaxy surveys, we ask the natural question, can we test the Hubble tension in a way that is independent of the CMB? And our BAO measurements work in a very similar way. So with measurements of baryon acoustic oscillations, here we're looking for the imprint of those sound waves in the matter distribution. So you have this preferred clustering scale at the sound horizon. And you use this as a standard ruler. And so this means, the BAO can constrain the size of the standard ruler, as well as some anisotropic stretching. And to know the value of H0, you need to be able to calibrate that standard ruler. So in other words, you need to break this degeneracy on the bottom of the plot between H0 and RD. So if you did something funny to RD, then you would change the value of H0 that comes from these BAO measurements. And so this is sort of a motivation for looking for probes of H0 that are independent of the sound horizon. And this is not the first time that people have thought about doing this. So Baxter and Sherwin first proposed an independent standard ruler, independent of the sound horizon, using the quality scale in the power spectrum. So this is the turnover in the power spectrum coming from the change between modes that enter the horizon in matter domination and modes that enter the horizon in radiation domination and have their growth suppressed until matter starts to dominate. And so this is a distinct scale from the sound horizon, and it has this very distinctive imprint on the power spectrum. However, if you and then they've gone out and they've tried to measure this equality standard ruler basically by modeling the power spectrum and then adding a parameter to marginalize over the sound horizon. However, something like early dark energy, in addition to potentially changing the sound horizon, can also modify the power spectrum shape. And therefore, it can, if you try to do this sort of measurement in an early dark energy cosmology instead of a lambda CDM cosmology, your H0 from the equality standard ruler would shift. And that is on the left. I've highlighted in red some points showing basically how things can change from a lambda CDM model to an early dark energy model. So our proposal is sort of a third measurement. So in addition to the sound horizon measurement and the quality scale measurement, the third way of getting the Hubble constant, essentially from galaxy surveys, using the amplitude of the baryon signal. So we start with constraints on omega BH squared from Big Bang nuclear synthesis, and that basically comes from baryon to photon ratio and the CMB temperature, which we measure extremely well. And then over on the right, we have constraints on the late time geometry. So this is essentially the anisotropic stretching of the BAO. This is totally independent of the value of the sound horizon. But this can constrain the value of omega m in a flat lambda CDM cosmology. And then to tie them together, you need the baryon to matter ratio. And we can get that from the amplitude, essentially, of the BAO feature in the galaxy power spectrum. And here I'm showing how this fractional peak to drop height of the BAO oscillations compares to the baryon fraction for a bunch of linear power spectra with different values for H and either a lambda CDM or an early dark energy cosmology. The point here is that the baryon fraction, the BAO peak to drop height trace each other very well, regardless of whether the model is lambda CDM or early dark energy. And this implies that this sort of measurement can be quite a robust way determining the baryon fraction and therefore the Hubble constant through this process. And so here I'm just showing sort of the difference, a schematic view of these different constraints. So the standard, quite constraining Hubble measurement is coming from the size of RD in the BAO, so the spacing between the peaks. And then this equality scale measurement is coming from the shape of the turnover. And then our new method is coming from the amplitude of the BAO oscillations. Okay, and then
Can you
yes,
tell me where you get m naught from?
we get that from the sound horizon marginalized distances at late times. So essentially, that means from like the anisotropic clustering of the BAO, but more importantly from ratios of distances, like the ratio of the distance to the Boss galaxies and the Boss-Lyman alpha forest, because that covers such a wide redshift range that has a strong, so the H part drops out, the RD part drops out, it only depends on the megamatter.
Usually one gets at best omega H. And then, of course, omega H squared comes from CMB, which you're trying to say we aren't even going to worry about that because it has a dependent. So the other physics that's going on, it's not exactly beta though. It's, anyway, we can talk about this later, but just wondering what, for example, what is your value of omega n naught?
It's like 0.3 plus or minus 0.298 plus or minus 0.01.
298.
And we also get some, we use supernova as uncalibrated standard candles. This also helps quite a bit. The constraining power is similar from the supernova and from the uncalibrated BAO. Okay, so we measured the BAO amplitude by splitting the transfer function into baryonic and CDM components. So here's this classic movie showing the evolution of acoustic oscillations. And so you can see this baryon peak forming as the acoustic wave stalls, the photons propagate outwards, and then the dark matter and baryon eventually resemble each other as you move to the shift. And so we sort of introduce this amplitude scaling parameter as a new parameter that's splitting the transfer function. And this is to isolate the effects of just the BAO amplitude from other effects of omega B, like changing the sign horizon. And then we performed two different types of fits to the galaxy power spectrum. So both a sort of template style fit and a style of the classic BAO fits, as well as a full shape perturbative fit. And in both cases, we add this extra parameter into the linear power spectrum, and then either apply the Gaussian damped BAO model, the template fits, or calculate all the perturbative terms for the full shape bits. And so this is just showing sort of the difference between how these fits work. So these BAO template fits, you have a fixed parameter, and then you have scaling parameters that allow the BAO to shift left and right. We have also added a scaling parameter on the amplitude of the BAO. And then you have nuisance parameters that are meant to account for all changes to the power spectrum shape that are not oscillatory. And this is encapsulated via a simple set of polynomials, or by a somewhat more complicated set that the DESI collaboration has used, and that we're now looking into using And yeah, whereas in the full shape fits, of course, you can vary the cosmological parameters. The template fits method allows us to model the reconstructed BAO. That is not done in the full shape method. The full shape methods have it's a much more complicated model of nonlinear galaxy clustering with nonlinear evolution and galaxy bias. On the other hand, in the template models, we're trying to model the reconstructed BAO, where reconstruction has gotten rid of a lot of these nonlinear shifts, and we have a simpler model for the nonlinear parameters. That should actually be like a simple, not that the nonlinear parameters aren't there, but we have them in a simpler form. On the other hand, these template models are considerably faster than the full shape fits, and they're less dependent on the model, since we're trying to use this marginalization, these sort of extra nuisance parameters to marginalize over anything that can change the shape of the power spectrum beyond the BAO. Okay, so BAO reconstruction, just to explain what that is. So reconstruction allows us to sharpen the BAO peak and increases detection significance. So the linear power spectrum at early times has this nice BAO peak, which is then degraded by nonlinear structure formation. And then essentially by sort of adding some displacement fields to allow you to partially move back to the linear peak, you can get a post-reconstructed BAO that is closer to the linear shape. So the correlation functions are shown in the lower right. You can see that they get more spread out before reconstruction, and then they get recovered more sharply after reconstruction. There's also a shift in the BAO that's induced by nonlinear structure formation that is very hard to see on this plot, and that is reduced after reconstruction. Okay, so this allows us to have 3 independent pipelines with this new parameter, both. So we try this template fit both to pre and post reconstruction correlation function, as well as applying the full shape fit to the pre-reconstructed power spectrum. So here I'm just showing those data vectors that we use, and you can see that the post-reconstruction correlation function does have sharper BAO peak in real data, as I promised on the previous slide. All right, so we test this pipeline on a large number of n-body mocks using these n-series mocks. They're large volume n-body mocks matching the geometry and size of CMAS. And we can see that this new parameter is recovered quite reasonably well, so within 0.4 sigma, as determined by the error bars on, from loss. And then here,
Can we just go back to
yeah.
with the gamma B? Sorry to interrupt so much, but it's a great talk. It's really up our alley here. So, gamma B, as you define it, is associated with linear transfer functions. And yet, you're using the nonlinear n-body, which means that there is sort of a transfer function, but it's a lot more complicated.
Yeah.
Are you steering clear of any of that nonlinearity, or are you accounting for it?
Yeah, so that it depends on which of these models you're using. So in the full shape model, we change the linear power spectrum, but then we use that modified linear power spectrum in the equations for the nonlinear terms and the higher bias terms. So in that way, we're accounted for.
You change gamma B and then you do n-body?
No. Then we calculate the PT coordinates.
Nonlinear correction.
Yeah.
And no gamma B in it.
Yeah. The n-body was already run without.
Yeah, but it was for the standard.
Yeah.
Case. And on large scales, we at least think we have gamma B, or sorry, T, E, basically TCM. It's only on short scales where it differs if it's a transfer. So, so I'm not quite sure how you're doing that separation. Or are you saying, I mean, you could be taking into account interesting effects, but they wouldn't fit into the linear theory or the way you've done the modification transfer bit power.
Yeah. I mean, we're only trying to take the changes in the linear powers, I mean, through the modifying the ratio of the transfer functions.
I'm so sorry to interrupt. Just given the time delay, maybe we should delay that discussion later, if that's okay.
And just actually one last thing, just to say, in the post-reconstruction model, the so there we're modeling this sort of the standard BAO, standard template fitting BAO way, which, and this is sort of less, it's less sensitive to nonlinear shifts, but yeah, maybe actually, yeah, okay, I'll talk about this later. That's more subtle than I really wanted to say. Yes, so I think I'm just going to, since we're at 4 o'clock, I think I may just skip to the last few slides. So after we showed that things were working both on MOX and on noiseless theory vectors, we applied this pipeline to the BOSS data, and we did this in various redshift bins, and there's some scatter between the different methods and between the different redshift bins, but this is all generally consistent with the scatter that we see on the MOX, so fitting to the MOX in different redshift bins has a similar amount of scatter. And within the error bars, all of these measurements are consistent with each other. And so then when we combine with the BBN measurements of omega BH squared and BAO measurements marginalizing over RD plus type 1a supernova, we get these constraints on the Hubble constant, this is a table, and then we should just go to the plot. So the current constraint on the Hubble constant from this measurement is rather weak because our measurement of FB is not, it's sort of low signal to noise. And so the measurement itself is consistent with both low and high redshifts. It's not very, the result itself is not very exciting, but I think the interesting thing here is having this technique available for future data, which is going to be a lot more constraining and will have a lot more volume than BOSS. And we expect the constraints to be better in the future by a factor of about 3. And so currently we're working on applying this method to both DESI and Euclid data. And that should be very exciting by the end of these surveys. And so I think with that, I will leave it at the summary slide.
Let's thank our speakers. Or people can stay here. But let me just check if online people have any questions too. If online people have any questions, please leave it in the chat. Any very desperate question? Okay, if not, let's thank our speaker again and we can have cookies and continue the discussion.